First of all, many thanks for this opportunity. Today, I will introduce to you spaGO, a self-contained machine learning and natural language processing library in Go. But let me first introduce myself. My name is Matteo Grella, and since 5 years, I'm trying to apply the artificial intelligence to save lives. For that, I'm cooperating with the EXO group, building a system capable to detect global security incidents in a short time from online media, matching them with traverse location, and automatically initiate emergency measures. I'm a researcher on natural language processing and related machine learning algorithms with a strong focus on dependency parsing. So now, what is spaGO? spaGO is a work in progress open source project initiated by EXO members. It's a self-contained machine learning framework completely written in Go, designed to support relevant neural architecture in natural language processing tasks, such as text classification, name entity recognition, question answering, dependency parsing, semantic parsing, automatic summarization, and sentiment analysis, and even in the next future, automatic translation. And that spaGO is really the first pure Go implementation that I know of capable to train, load, and perform inference on state-of-the-art models. So why did I create spaGO? Well, first, I wanted to learn Go. And also, I wanted to refresh some basic concepts of machine learning. So I thought, why not combine these two objectives and try to develop from scratch this library so that also other people can benefit from that for educational purposes. So in spaGO, you will find some dependencies, most of them are manual utils. And things start working pretty well. So the overall scope of the project brought to a comprehensive production-ready NLP library, where I also took care about stateless server, TLS encryption, gRPC communication, Docker containers, all the things that in my day by day, I have to use in production. And with all of this, I'm trying to build with high quality implementation, following some principle from clean coding. And as Go doesn't have a rich machine learning and natural language processing ecosystem, I'm sure with your help, spaGO can fill this niche, providing the most important architecture in this field. spaGO ships with a lot of features. I've got inspirations from a PyTorch framework in terms of automatic differentiation using a defined by run approach. spaGO has built-in optimizers from the basic stochastic gradient descent to some powerful variants of this, like the Adam, Radam, RMS prop, AdaGrad, etc. We have feed-forward models such as linear model, highway, convolutional models. We have recurrent models from the most famous long short-term memory, or LSTM, which is a really powerful type of recurrent neural network. We also have the gated recurrent unit, or GRU, attention mechanism, really crucial components for state-of-the-art language models. So in spaGO, you will find self-attention, multi-head attention, memory-efficient word embeddings implementation using the Badger key value store library, also that written in Go. Up to more complex and sophisticated architecture to perform text classification, sequence tagger using a bidirectional LSTM with on top a conditional random field, some algorithms to perform name entity recognition and question answering, etc. And I will soon provide the state-of-the-art implementations for dependency parsing. So, but the most important feature of spaGO that make it ready to use is its compatibility with PyTorch models. Not in general, but in particular with Flair. Flair, provided by Zalando Research, is a state-of-the-art multilingual sequence labeler architecture for name entity recognition and post-tagging, or even for text classification. And spaGO is also fully compatible with the Hugging Face transformers. Are really amazing company. Hugging Face provide high quality code, and they release more than 30 pre-trained models in more than 100 languages. And we can benefit from those pre-trained models, pre-trained neural models inside spaGO. spaGO is not perfect yet. There's no support for GPU, and spaGO is not GPU and TPU friendly by design. As it started for educational purposes, I thought, let's keep things simple. So instead of using dynamic tensors, in spaGO you will find only two-dimensional matrices, from where we can use vectors and scalars as a subset of. So it's on the roadmap, huge redesign on subcomponents of spaGO to allow batches operation. Because if you don't have, if you cannot perform batch operations, you will not benefit on the GPU. And even for the CPU, we have some constraints. So we are far from the amazing optimizations available in mainstream deep learning frameworks such as PyTorch or TensorFlow, in the way they represent data and store data inside tensors, and the way they perform efficient operation, thanks to the batches. So with all this, where would I use spaGO? I already assume we can increase the speed on a CPU inference, probably together. Again, I ask for your help. And currently, PyTorch is around twice faster, especially for large matrices. But already now, spaGO is not as slow. We rely on GoNAM assembly code optimized for MD64 architecture. So indeed, it's quite fast for some linear algebra operation. We are experimenting to integrate the fast Intel machine learning toolkit using Apache Arrow to take advantages of shared memory rather than using spaGO. That, as you know, it's a bottleneck in our Go world. But most of all, I'm sure that spaGO will really succeed if we can create and benefit from sparse models, high sparse models, rather than dense models or billions parameters, which doesn't make any sense to me as a long-term direction on the artificial intelligence. So I'm a big fan to create a smarter model, a smaller model, using smarter algorithm, for example, with local sensitive hashing, or using some prior knowledge. But that's all on the roadmap, and I will be really happy to discuss all of this with you. With spaGO, you can also train your own not very deep model. For not very deep, I don't mean just an input and the output connections. I mean, you can create some sophisticated neural models, and you can train directly in spaGO. On top of this, I think that the training stage is a little bit less interesting for production use, as even if you have GPUs or TPUs, it will take weeks or months to create or to train a state-of-the-art language model. So why don't benefit from pre-trained model? And that's the approach we are using on spaGO. For instance, in spaGO, within the CPU, you can already now train shallow models. As I said, shallow models is not really input-output connections, but with some intermediate layers, you can definitely fine-tune the deep models, especially if you are okay to train maybe the top layer of your deep model, and you can definitely perform inference. And the inference you can perform with really good state-of-the-art results thanks to the automatic importing of weights from PyTorch models. And all of this is already included in the current version of spaGO. So I think you got it. My presentation is quite technical, and I will go forward with that. So you will have at the end of my talk a good understanding about what spaGO is and what this library contains. So the building blocks for the lightweight internal machine learning frameworks are four packages. The first one is the mathematical package. As I said, I implemented from scratch two-dimensional dense and sparse matrices where vectors and scalars are a subset of. They are almost full test. not really fully, but it's 80%. All the basic linear algebra operation are tested, so the addition, multiplication, division, and production. I mean, it's all tested. As a data storage, I decided to go with a slice of float 64. Of course, that was exactly the point where I missed generics in Go, because using float 32 will be much faster, probably twice faster, but I didn't want to replicate code. And all what about memory consumption and increasing speed, that would be next step. As I said before, we use GoNum, which is a library. We imported some piece of code of GoNum library directly inside spaGO, because I didn't want to have a lot of dependencies. So I tried to really stick with a minimal approach, preferring to import code directly into spaGO. And we need that to perform linear algebra operation with assembly code. At the end, really important, as the internal machine learning framework uses a lot of matrices. Every time for computation, we need a new matrix. We use a regressive buffer techniques using a sync pool from the standard library for efficient reuse of pre-allocated memory. So we actually have a minimal overhead. And this is even more clear for the second package, which is the AutoGrad package, where we find a graph. And of course, if we have a graph, then we have the nodes. And the nodes of the computational graph are mainly a variable nodes that you can think like a wrapper around a matrix, and the operators nodes. And for the operators nodes, I mean addition, multiplication, hyperbolic tangent, the ReLU, concatenation operation. And for the overall operators, I implemented the forward formula, the forward equation, but also all the derivatives. So you can perform with the AutoGrad package the automatic differentiation. Also, this package is almost fully tested. So when you use spaGO, you are sure that the forward computation and the derivatives are, I would say, they are correct. And thanks to the automatic differentiation, it's exactly the point that allowed to enable training of your models through backpropagation of gradients. And in spaGO, you will find the basic backpropagation, the backpropagation through time, and even a clear implementation of a truncated backpropagation through time. So as we have gradients, we need to use that gradients to optimize our model. So I had to implement some optimizers. And those optimizers are all based on gradient descent from the stochastic gradient descent, where we just define a learning rate, maybe the momentum, and if we like to have the necessary momentum, but also more sophisticated models like Adam, Radam, RMS Prop, or AdaGrad. On top, I had to implement the K methods or gradient clipping or other regularization techniques to try to avoid some common issues when you have to deal with gradients. I also tried different approaches for optimization, for params optimizations. For instance, in spaGO, you will find a package for differential evolution that brings concepts from genetic algorithms such as population, crossover, and mutation. I'm still experimenting on it to understand the full potential, but I think it's definitely an interesting approach to optimize a neural model. And in terms of neural models, we find the package neural network, where you will find actually three main pieces. First, the parameters. That could be weights or biases. They are optimizable and serializable, because at the end of the story, you train a model and you want to load back your model to test it or to perform inference, most likely in production. Then you find the model, and you can think of a model like a container of parameters. So the model will contain a sequence or a series of weights and a number of biases, and it can contain other models. So with a model, you can mix parameters and submodels to create more complex architecture. And the model has an important role, which is to instantiate a processor. The processor, the reason why I had to introduce this concept, which is not common in machine learning, in mainstream machine learning framework, is because Go doesn't have much magic, and I want to keep the implementation straightforward. So I came to a point where I had to connect the parameters, like with the weights and the biases, within the graph, because the parameters are fixed, especially once you train, you serialize, they're fixed, where the graph, the purpose of the graph is to support the forward computation of your neural model. So the processor creates this bridge to connect the parameters within the graph for the forward computation. Moreover, the processor take care about the state for recurrent models, so it's really suitable, just the single processor for perform feed-forward operation, convolution operations, and recurrent models. To make things more concrete, a toy example. Toy example to perform a simple addition. So this is the basic formula we want to solve, C equals A plus B. So to do that, and especially to have gradients in case of backpropagation, we have to instantiate a new graph, we call G. Then we instantiate two variables, which are nodes, with the G, new variable, wrapping, as I said, a new matrix, which is a scalar, of is one single element this time, with value 2. And the final true, this argument is to say, yes, this node will have gradients. So you have to consider in the automatic differentiation operations. Same story for the node B. You have a new variable, wrapping a new scalar with value 5. And then we create another node, and this node is not anymore a variable, but is an operator node, for instance, an addition node, where we ask the graph to perform the addition of A and plus B. And we can print the results, and the calculation is actually performed there with the define by run approach, which is different than TensorFlow, that first you have to define the graph, and after that you can run this graph. Now here you write your code with your control flow, and the operation are actually performed. We can ask the graph to backward that node with arbitrary gradients, for instance 0, 5, and because of the properties of the derivatives of derivative of the addition operation, then we have the same gradients back to the node A and the node B. It's arbitrarily complex, the type of formulas or the way you can mix nodes and operations in spaGO. Here we have one of the most important operations in machine learning frameworks, which is the affine operation, where you have a bias summed by with an arbitrary number of weights and inputs multiplication or dot product. And if you notice on the right side in this picture, you can really see the minimal overhead of the overall graph construction compared to the final operation, which is the only one that actually takes time. And this is what we expect. So the generic matrix vector multiplication is the only operation that takes time, meaning if we improve this operation, the overall performances of spaGO will benefit, will improve. This is an example of the most common layer that every machine learning framework must have, which is the linear model, also called the dense model or dense layer. And the linear model contains two parameters, the weights and the biases. So we instantiate with this new constructor a new empty model. And as I said, the role of the model is to instantiate, other than contain the parameters, is to instantiate a new processor. The processor will be instantiated within a graph. So if you look at the processor structure, you will see the base processor, which is my way to avoid boilerplate, nothing really important right now, but you have to note the weights and biases nodes, which are instantiated here as a new wrapper from the model parameters. So in that moment, the weights and the biases become nodes that we can finally use in the forward computation, in this case with the affine operation. Building a multi-layer perceptron is really simple. It's just a concatenation or a stacking of linear layers with intermediate activation or transformation functions. For instance, we have the first layer here, the input layer, then the hyperbolic tangent as activation layer, the output layer activated with the softmax operation. I will not go in too many details for this slide. This is just to show how much it's simple to transform equations. So your basic formula, in this case for the LSTM, the long short-term memory recurrent unit or recurrent network inside spaGO. So basically the same way you will read this mathematical formula, then you can read and understand with a first glance the spaGO code. So to put the pieces together, this is an example. In order to make it working, you will need some more instructions, maybe to introduce epochs and something more. But in general, the basic steps are to define a model. In this case, the model is a new linear model. Defining the optimizer. In this case, I created optimizer with the stochastic gradient descent, nothing fancy, with just a learning rate, no momentum, no necessary momentum. We connect the optimizer to our model of interest. We define our criterion objective, which is the final training objective or training goal. And then here I hope you will start getting the structure of spaGO. We create a new graph. We ask the model to instantiate a new processor connected to the graph G. We ask to perform the forward computation from arbitrary input feature. And we back the for operation returns the predicted output. After that, as a forward computation, we calculate the loss with the mean square errors, in this case, matching the predicted values with some expected values. And after that, we can ask the graph to automatically calculate the self-derivative respect to the loss node itself, and backward all the way back to the leaf nodes, in this case to the parameters, so we can ask the optimizer to optimize our model. So this means that the backward operation will insert the gradients inside the model parameters that the optimizer can use to perform the final optimization. This is an example for natural language processing, in particular for the Flair architecture by Zalando research of sequence labeling. And you can actually see with these two colors how close is the Go spaGO implementation with the design, with the picture of the architecture of the original paper of Flair. So on the top red part, we create a tagger layer with a bidirectional neural network, including left to right LSTM and a right to left LSTM that we concatenate. We make a score to reduce the dimensionality and actually to score, and a final CRF or conditional random field layer to perform the final prediction, so to retrieve the final labels. Same story for the blue part, which is the contextual word embeddings, I would call it this way. You can create arbitrary complex stacked embeddings models, concatenating, for example, the pre-trained global or word2vec embeddings. You can also uses the original implementation, the contextual string embeddings, using pre-trained left to right and right to left character language models, and reduce the dimensionality with a projection layer. Not so different, the overall principle from the BERT layer. BERT layer has been introduced, the fundamental of the BERT technology, with a paper that, to my mind, was called "Attention is All You Need," and indeed is really attention-based model to perform sophisticated natural language computations. And as I said, the model can be combined, can be created using sub-models. And so each of these share the same interface, the same model interface. The model creates a new processor, and also here we see how the same graph is shared by the overall sub-processors to use the same graph for the final forward computation. In this case, we use a post-normalization with multi-head attention and a feed-forward network. So I think I described a lot theoretical part of spaGO, and I think it's right time to show some demonstrations. So you need only 5 steps to build spaGO, build the model importer from the Hugging Face repository, and to run the server for question answering, for example. So let's have a look about how question answering can work on your laptop. I use Insomnia to show the basic HTTP JSON API. This is the route, so it's the answer route. We define a passage. For instance, Matteo lives with his wife in Turin, Italy, and we ask a question: where does Matteo live? When we submit, it takes a few seconds, and we get the answer. And the answer is Turin, Italy, with the span, so we can indeed we could highlight the piece of the passage that include our answer with a confidence level. So I decided to make the demonstration just a little bit nicer to explain better the capabilities of spaGO. This UI is provided by the same spaGO library, the same HTTP API. I will copy and paste a piece of text from the page, the Wikipedia page of Google. For instance, Google was founded in September, etc. And I will ask a question. For example, who are the founders of Google? And when I press answer, we get Larry Page and Sergey Brin. So we have an end-to-end question answering system. Let's try another question. Where did Larry Page get his master's degree? Stanford University. And I think it's quite remarkable. I think we will have some fun playing with this tool, because if you notice, there are no words like master or degree, but yet the power of the BERT model of the NLP, latest NLP technologies are enough to retrieve the right answer. In this case, Stanford University. The other demonstration, I promise you, was about name entity recognition. So here, really closer address is just, same address. I just run this server in another port. I copy and paste the text here, and I press analyze. And in a few seconds, the system will extract the overall organizations, the overall persons and locations, where we might also want to drill down and to visualize single occurrences of different entities. For instance, the first Google, the Stanford University, the Alphabet as organization, or the occurrence of Larry Page, Sergey Brin, Sundar Pichai, or the California for the locations. So I think you will have some fun, and the more you get experience with spaGO, the more you might want to help me to growing this project together. So to recap, spaGO started for educational purposes, so I try to keep the code relatively simple and quite succinct. You definitely don't need to be a mathematical or machine learning expert to understand spaGO, and I think it's your opportunity to understand what's going on under the hood of the artificial intelligence. It's absolutely easy to use, especially if you have a Go project. spaGO is a Go module, so the integration will be straightforward. If not, or if you prefer, you can use, as I showed you, the HTTP API with the TLS encryption, really suitable for production use. Even better, you might use the gRPC, that using the protocol buffer is much faster than the HTTP API, the JSON HTTP API. If you are too lazy to just copy and paste the static link binary of spaGO, you can use the Docker container. It's really as you prefer. And I think that, again, especially with your help, with spaGO has great potential to perform fast inference of natural language processing models on the CPU. And it's on the roadmap exploring some Go potentials, for example, concurrent computations with coroutines, with channels. I already using some of these technologies, but not to the full extent. So I think it's really a lot of space to improvement. spaGO is not stable yet, but is growing rapidly, even in number of stars. In a few days, we reach more than 600 stars. We have a few forks, a few pull requests. Even the number of active contributors are increasing significantly. We use the main branch to always have running environments. So as I said, maybe in the beginning of my presentation, you can force spaGO, you can clone spaGO, and start using it using the main branch. The overall code coverage is only 60%, but we will improve. In order to build spaGO, we had to build some sub-projects. In particular, my colleague Marco Nicola is the main contributor of 3 sub-repositories. One is GoPickle, which is the library that allows spaGO to load Python serialized data without touching Python. So you can avoid to install Python in your machine if you don't like it, and with just spaGO is more than enough to load Python models. Go tokenizers, it's an attempt to port the Rust implementation of the Hugging Face tokenizers inside Go. And GoSlide is an attempt to port the C++ implementation of a high-performance, deep learning, highly sparse framework for the CPU inside Go. And I already assume that we will use most of them inside spaGO to improve the overall performances. So many thanks for your interest. I hope I was clear enough with my strong Italian accent. If you like the repo, please leave a star to show your support. You can write to me privately, but even better, you can write an issue on the GitHub repository. Many thanks again.